So last time we talked about the reparameterization of the smoothness measure in terms of full width half maximum, and there was a little bit of a discussion between the three of us whether this term actually plays a role in imaging, and I said it's in the SPM table, and then Lilla, I think, also looked at it. So here, down here, it's a little bit small, but you're also sitting miles away. We find this term full width half maximum, which has been estimated here. So the full width half maximum parameterization of the smoothness plays a role. And then, and this is why I'm bringing this up, there is the other term Riesel in here. So you see Riesel here and you see Riesel there. The aim for the next 2 hours, essentially, I guess, is to talk about volumetrics, measuring volumes of excursion sets, and or in other terms, introducing this term Riesel. Yeah, and I'm just bringing this up to show you that I'm not doing the whole thing for fun, and that this has nothing to do with brain imaging, but you see it in your brain imaging results. And you also see that in FSL, although it's a little bit less visible. Good. And then So then what we want to talk about today is essentially the notion of Riesels. And the whole thing is about measuring volumes, or how I call it here, volumetrics. I don't know whether this term exists, but I found that it nicely summarizes what this is about, because it's all about measuring volume. And the last thing that we want to talk about are these Riesels that you just saw in the SPM results figure. And to get there, we have to talk about intrinsic volumes. And to get to intrinsic volume, we have to talk about Lebesgue measure, or Lebesgue volume. Measure. So the whole thing is quite hierarchical. So the first things that we talk about might make you believe that this is not really about brain imaging, but then as we proceed and actually end on the term Riesel, we are in brain imaging, and essentially brain imaging only, because Riesels, I don't think they exist anywhere else than brain imaging. So as I briefly mentioned at the end of the last session, the whole thing is about two things. So one thing is to allocate a notion of volume to arbitrary geometric objects. So the question is, what is the volume, for example, of such a thing? And you know the volume of a square, or the area of a square. That's also what I said in the last session, that when I say volume here, I mean the appropriate thing in the appropriate dimension. So if you're in 3 dimension, I mean volume. If we're in 2 dimension, by volume I mean area. And if we're in 1 dimension, by volume I mean length. The first 2 bits are essentially about how to ascribe volume to things. Or geometric objects. And then the last thing, and that's fairly important, and the motivation for the whole thing, is that Riesels, or more general Lipschitz-Killing curvatures, allow for describing a smoothness adjusted volume of a geometric object over which a random process extends, Why is everybody coming on their own? Why don't you just come all together, like 10 minutes after or whatever? Anyway, so this is about smoothness, adjusted volumes. And this relates to, of course, volumes of domains of random processes or random fields. So the question is, what is the volume? So what is, in this case, the length of this line? If you adjust for the properties of the random process that extends over it. And we will see how this is done. It's actually quite simple. So you basically ask yourself, so if I have a unit volume, then I scale this unit volume by the smoothness, and then if I have more than a unit volume, I just multiply. But we will get there, and we will see how that exactly works, which will, of course, be based on this full width half maximum reparameterization. Good, and then this whole topic of volumetrics, it really is kind of it forms its own mathematical niche. So especially these intrinsic volumes, they are definitely, from my perspective at least, in a mathematical niche that deals with essentially modern geometry. So how in modern times we are able to ascribe volumes to geometric objects. And what we do in this section is more to have a very superficial glance at this mathematical field and say, okay, that's what people who are experts in this deal with. We don't understand really the details and we cannot work there, but we have a rough feeling of what they deal with, which means that the whole thing will work that we look at the definitions that they use and then try to make some sense out of them so that we know at least a little bit of the concepts and the terms that they use. Good. So then the first thing is Lebesgue measure, which will also feature again when we talk about the probabilistic aspects of excursion sets in the subsequent session, because the expected volume of an excursion set actually is measured in terms of Lebesgue volume or Lebesgue measure. So Lebesgue measure is a very fundamental mathematical function to ascribe volume to subsets of the real numbers. So you always have to think now that if we think about geometric objects, we model them as subsets of the real numbers. So for example, if you have a three-dimensional object like this cup, then you would in mathematical terms describe the whole space in terms of the real numbers to the power of 3, and then this cup somehow is a subset of this three-dimensional real space, and the aim is then to somehow say, okay, this has the volume so and so. And Lebesgue measure, as we also discussed briefly at the end of the last session, derives from a desire to ascribe volume to such objects. And then in mathematics, if you want to come up with measures or functions that give you a value for a certain thing, you desire certain things that basically conform to intuition, and these things for Lebesgue measure we briefly discussed at the end of the last session. They are first that Lebesgue measure should be compatible with the notion of length area and volume in the respective dimensions. So essentially, if we are in R1, we want the Lebesgue measure or the Lebesgue volume to correspond to the length of an object. If we are in two-dimensional space, we want the, so if we have a two-dimensional object, we want the Lebesgue measure to correspond to the area that the object inhabits. And if we are in three-dimensional space, we want the Lebesgue measure to describe the volume. Compatible with these things for, and that's important, for lines, so for lines, rectangles, and cuboids. So Lebesgue measure is, of course, more general and can be applied to more complex geometric objects than lines, rectangles, and cuboids. But at least for lines, rectangles, and cuboids, for which we know how to compute the length, the area, and the volume, we want they wanted the special case of Lebesgue measure to come out as the familiar things that everybody knows. Then we had this thing that Lebesgue measure should be smaller for object or subset of R to the power of 3 maybe, for object A than B, if A fits into B, whatever that really means, but it's at least intuitive. So if you can somehow put, if you have some object A, and you can put, if you have an object B and you can put an object A into it, then the smaller object that you can put into the other objects should have a smaller Lebesgue measure. It should be invariant under translation. That means if you move the cup from here to here, it should still have the same volume. Invariant under translation. And finally, additive for non-overlapping objects. So if you have this cup and this mouse, then the volume of the cup and the mouse together should be the volume of the cup plus the volume of the mouse. So I think these desiderata are fairly okay to understand. Then you of course can say, but and we discussed that briefly at the end of the other session, what happens if the objects overlap, what do you then want, and so on. The point I'm trying to make with this desiderata is that although the definition of Lebesgue measure, which we will discuss in a second, is relatively complex, the aim is only to have a mathematical expression that fulfills certain fairly intuitive aspects with respect to measuring volume. Yeah. So if you don't like to, maybe you've seen the study questions for this section, they are really on the intuition of these things, not at the formal definition, because these formal definitions are relatively long. And also there's not much to gain in this part of the course from the exact formal definition, because it's more important that you actually get the idea that this is just a mathematical formulation of trying to measure volumes. And so then let's look at the formal definition. And you will also see that the definition of Lebesgue measure is actually, the starting point is actually relatively straightforward. So you should not be afraid of Lebesgue measure. because it starts with something really familiar. So let R be a closed rectangle, so in d-dimensional space. So I will tell you in a second after writing this up what this means visually. It's a subset of RD. I printed out the thing again because there were a number of typos. There might still be, but especially in this section there was N and D all over the place. So I tried to clean that up. So let R be a subset of RD with minus inf t RD kleiner gleich BD kleiner gleich inf t D gleich 1 to B. Denote be a d-dimensional rectangle with sides parallel to the coordinate axis. So that's something, I also visualized that in the figure, but it's something that you're really familiar with because it's just a rectangle, at least as long as you are in 2D. So if you're in 2D, you have and you have two intervals here, A1, B1, and here A2, B2. Then these two intervals, if you look at their product in a Cartesian set sense, then this just means this rectangle. And the only maybe complex thing in this first thing is that you now should also imagine rectangles in 3D, which you would normally call cuboids, but you can of course also call them rectangles if you want this definition. You can also have, of course, lines in 1D, and you can also go to higher dimensions, and you can still talk about rectangles in 5 or 6 dimensions. But it all really relates to your two-dimensional intuition of rectangles. So that's quite straightforward, right? Are there any questions about a rectangle? No. Of course, you need somehow to know what Cartesian products are, but I think this is relatively clear. Then let R, and then the definition just uses the set of all these rectangles. So of course you can already in 2D, whenever you change the A1, the B1, the A2 and the B2, you get another rectangle. So you can define a set of, let R denote the set of all rectangles. In RD. That's straightforward. And then let can also, I think in the definition I used a very long sentence, but you can also read this as multiple sentences. Let the volume of a rectangle given as the following function phi. So this is a mapping from the set of all rectangles in d-dimensional space, so all possible rectangles, for example, in 2D space, to the set between 0 and not quite infinity. So you cannot have an infinite rectangle, at least in the current definition here. And what this function does is that it allocates to each rectangle, here R, a volume, which is called the volume phi R of this. And now this volume is shouldn't really be surprising to you. It's given as the product of the difference between the ends of these intervals. So let's look at an example. So if we have this thing here, 1, 2, 3, 4, 5, and we have slide here 2, 3, 4, 5, and let's say we have a 1 equals 1 and b1 equals 5, a2 equals 2 and b2 equals 4. Like this, right? What's then the volume of this rectangle? According to this formula and according to your intuition? Sorry, what? 8? Yeah, I would say so as well. Because the side length here is 4 and the side length here is 2. So that's, if we want to apply this formula, we can do, of course, 5 minus 1 times 4 minus 2, which is 4 times 2, which is 8. Yeah? So and this is of course just the width times the height of the rectangle. Yeah. So this rectangle volume is really something that you have learned about. I don't know, when you were, I don't know, 12 or something. When does one learn this? I don't know. And one can now debate whether this is a good volume measure for a rectangle, whether one would not rather have a different measure, but it doesn't feel really like something that is negotiable somehow, because one is very familiar with that. Of course, but of course you can define another volume. You could also say the volume should be 4 plus 2. Actually, we will see that. That's actually the first intrinsic volume. But the typical volume or area in this case that is ascribed to rectangles is actually the multiple of these. Good. So this is something that you are familiar with. And now based on this formulation of the volumes of rectangles, Lebesgue measure is actually formulated. So it starts from something that is, I think, okay to everyone, and then it defines, and that where it goes then a little bit crazy is then Lebesgue outer measure. So it starts with the notion of what is called outer measure. Lebesgue outer measure is defined as the following. Again, it's a function, sorry, which I call lambda star, because Lebesgue measure will just be called lambda, and this now is defined on the power set of the d-dimensional space. So the set of all possible subsets, which makes some sense because we want to define a volume for subsets of R to the power of D, so a d-dimensional real space. And then, of course, it makes sense if we want to have a volume definition to be able to use this volume definition for all possible shapes or subsets of this space. Lebesgue measure doesn't quite achieve that. It only essentially works for a sigma algebra, and we discussed before that the sigma algebra on the RD is a little bit smaller than the power set, but for all things that we actually need in neuroimaging, where nobody ever talks about power sets and sigma algebras anyway, but me. But that's not quite true, but it's something in neuroimaging to actually talk about power sets and sigma algebras. For everything that we need from this perspective in neuroimaging, we can conceive sigma algebras and power sets as for the real numbers essentially have the same thing. So there is where we can actually be a little bit more imprecise. So we now want to ascribe volume to all possible subsets of d-dimensional space, and we allow also for infinite value. And these subsets are called S. In line with the idea of search spaces that we are later interested on. And this Lebesgue outer measure allocates a value between 0 and infinity to all values, to all subsets of real space. And this is defined as the infimum. If you don't like infimum, then think of minimum. The minimum of there's still a typo. Doesn't get rid of the typos here. The minimum from 1 to infinity of all the rectangle volumes. So in the script you see a mu there. That's of course wrong because it should be defined in terms of the measure of a rectangle volume that we just defined above. And because I got this from another source where this was called mu, there's a mu, but it should be phi. So it's the sum of all the rectangular volumes. And the question is of which rectangles? Well, of the rectangles, so that S is a subset of the countable union of all these rectangles, where the rectangles are, of course, rectangular things. So what does that mean? It's a little bit like what you did when you, for example, talked about the integral, where you in school, where you have you do these kind of step functions and put them in like these bars, and then you say, okay, now we make this even finer and finer, and then we get to the integral. So the Lebesgue outer measure is the smallest sum of rectangular volumes, the rectangles of which cover the object. So there's a figure in the script that has an object that looks maybe roughly like this. And then what this definition of Lebesgue measure says is that you first should consider rectangles that cover this set, so that S is a subset of this countable union. So the problem is that there are infinitely many actually possible ways to cover this with rectangles. So one way to cover this with rectangles is the following. And you see that these rectangles are partly overlapping, and there's another rectangle. Let's make a very small one here. And let's make a big one here. And the idea is with this that the volume of this thing in the background, this black shape, is now the sum of these rectangular volumes. The rectangular volumes we can compute. We just saw how we compute them. And that we sum them, and we should find the smallest value of possible coverages of this object with the rectangles. And this, of course, I mean, you could now think about writing a computer program that tries a rectangular coverage somehow, and then you try to shrink this step by step. But it's definitely something that one can intuitively kind of have a feeling, yeah, that is possible. So I can make the rectangle smaller, and then, for example, if I get so for example, I make this rectangle smaller, and then I still have this thing here, so there I can fit in two rectangles. But then I'm still not quite there, so then I have to find another coverage with a smaller rectangle. So one has an intuitive feeling this could be possible, but it's not that one can straightforwardly now say, okay, if we have this shape which are just drawn by hand here, this is how you set the rectangles, because that really depends on the shape and so on. And it's actually, also talking about that. This actually, if you are into Mandelbrot sets and fractals and so on, and measuring the outline of the coast of Britain, then these things of actually ascribing volumes and so on get interesting, because it's not necessarily the case that for every subset you can actually find such a rectangular coverage. And this is why actually the Lebesgue measure is then defined only on sets for which, for every A, the following holds: A S plus lambda, and somehow I don't get rid of this n there without S. Lebesgue measure is Lebesgue outer measure only for subsets S, for which for all A subset RD this stuff here holds, which again is not something that you can really test, because it now means that you, for all possible subsets of RD, you have to check whether this holds. And there are many subsets of RD, so it's again something that is nice if you can use it in proofs for certain things, but it's not something that allows you to now go and compute Lebesgue measure. And for such sets for which this holds, which then also can be shown to form sigma algebra, or the set of Lebesgue measurable sets, Lebesgue measure is defined as the Lebesgue outer measure. So essentially, the way this definition works is that you come up with a fairly abstract definition of what is called Lebesgue outer measure, and then you say, if I use this definition of Lebesgue outer measure for specific sets for which it makes sense, then I call this Lebesgue measure. Again, like I also say in the script, one cannot really go about and compute something from that. But I can tell you that under this definition, certain things hold. So, for example, a very popular thing is Lebesgue measure of an interval. This is something you see in probability theory all the time. So, actually, often any interval. So, Lebesgue measure of an interval, of an open interval, of a semi-closed interval and actually both of them, and of a closed interval. They all have the same Lebesgue measure, and that is b minus a. Yeah, so this is now in 1D, and if you have something, for example, like this, a b, where b is of course larger than a, then the Lebesgue measure of this interval, lambda a b, is equals b minus a. That this is the case, this follows from the general definition, but to get from the general definition to this is again work. So that it's not, you should not get the wrong message that these things that follow from that, or the desiderata that also can be shown that derive from this definition, that they actually hold, are easy to see. So you should not be feeling like or think that the way the script is written, that it's immediately clear that from this definition it follows that this is the case. This requires some pages of mathematical derivation, which you can actually find in one of these references that I give. I think in the Hunter reference, I think he actually shows that, for example, this thing holds from the Lebesgue measure, but it's not something that, so this is really more knowledge than understanding. But there is value in knowledge from my perspective as well. And I just wanted to give you a taste in terms of the definition. There is a definition, but it's fairly abstract. And abstract definitions are helpful for proofs because there you can sometimes use these definitions. You also have to think about how these definitions come about. So these definitions come about by people wondering, how can one show that from this something else follows? And then you start to think, and then you, at one point in the proof you come about something, yeah, but then I really, if this is supposed to hold, then I really need that, for example, something like this holds. And then if you put it in the definition, then of course, when you're trying to derive something, then you can use this because it was in the definition, but there was no real good intuitive reason to put this into the definition beside the fact that then the proof works. So it's always nice to try to understand abstract definitions in math also from an intuitive perspective, but you should also relax if this is not immediately possible, because sometimes these things are just there to make formal proofs work, and then you can waste a lot of time about trying to understand what this means intuitively, while really the person who wrote it just didn't think about any intuition, just thought about, okay, then my proof works, so I better put it into the definition. Okay, another thing that we will need in a second actually is that the Lebesgue measure of a closed ball with a radius r in Rd. So a ball is a ball in Rd is a set of values in r to the power of d for which the distance from the origin, which you can measure in terms of the Euclidean norm, so x minus 0, and the 0 is the origin, is smaller or equal to r. And the Lebesgue measure of such balls can also be computed, and in general comes out to pi to the power of d half divided by the gamma function d half plus 1 and r to the power of d. So this is essentially just a generalization of the familiar formulas for the area of a disk, which is what? What? Pi r square, yeah. 2πr is also a formula for something. I think for the circumference. R square, I think the what you can use here is R square sounds like area, so it helps to put that here. And for a ball, what's the volume of a ball? Can somebody Google that, please? I don't want to say something wrong, and I'm not completely sure about the values of the gamma function for this. So I know that it's r to the power of 3. This is what this says. Then pi, and then I think it's 3 over 2. 2 over 3. 2 over 3? I guess. Yeah, 2 over 3? 4 over 3. 4 over 3, yeah. This 4 over 3 follows if you evaluate the gamma function here. Yeah, so this should be a ball. And this is just the Lebesgue measure of these entities. So that's that, and that's that. And again, these are just the familiar, in principle familiar geometric volumes that you learned about in school, but generalized to d-dimensional things, and then expressed in one formula, for example, here for round things like disks and boards. Okay, I think this is a good time for a break, because then the next thing would be intrinsic volume. So are there any questions about this? So again, Lebesgue measure for familiar geometric objects, the desideratum was that this comes essentially out as the volume that you know for familiar geometric objects. And no, that's about it. Good, then let's have a break until 9 o'clock.